Okay, so the human retina has 3 color band sensitivities, basically the RGB, and this is why we have RGB in our video universe, okay? When you combine those 3 colors in different ratios, you can reproduce the colors of the spectrum and create the color that we all enjoy. That's visible light. Red, orange, yellow, green, blue, violet gets represented in those 3 color bands. Those are in the cones of your retina, all right? But suppose you want to take a photo of the universe in the infrared or in the ultraviolet, in parts of the spectrum that are human eyes not sensitive to. By the way, it was a great discovery to realize that we are practically blind. Roy G. Biv is a tiny slice of the full electromagnetic spectrum.
400 to 700, right.
Angstroms, right, nanometers. And that is a tiny slice out of a huge band of light. And so when we look at the universe, if you want to deduce the actual nature of the universe, you would be incomplete if you based it only on data from that tiny slice. So we figured out how to detect light from other bands of the electromagnetic spectrum. In so doing, let's say we have infrared. But now how do you take a picture and show it to somebody if you can't see the light? So what you do is you have an infrared detector, you have 3 bands. You don't care what wavelength those bands are because you can't see them anyway. Then we take RGB, assign an RGB filter to each of those bands, you can create a color photo. That is the color you would see if our eyes were shifted to the infrared part of the spectrum. So when we make color photos of bands of light that are not visible, we just slap an RGB to 3 bands, that's what you would see. Now, there are occasions where molecules in space emit very sharply defined bands of light, very narrow. Oxygen does that, it emits a green light. Nitrogen emits an orange light. So sodium is an orange light. So what you can do is, you can take a filter, slap it on that, then just information from that molecule is showing up in the photo. So now you slap an RGB to it, but now the G, for example, normally it's broad, but it's attached to one band, one narrow band of light. And when you do that, you punch out of the photo just those molecules. So you can use this as a way to highlight certain chemical features of a color photograph in space. And that's what we do, that's what the Hubble folks do. You can slap an RGB in any way you want, and that's what it would look like if your eyes had those sensitivities. And so false color is a different thing. False color is when you assign a color table to something that has nothing to do with color. For example, temperature, or rainfall, or anything that is not color, or you attach it to intensity. That would be false color. What goes on with the Hubble photos is not false color, it's shifted color. And it's because we can detect data much better than the eyes can. And so you gotta need some way to turn them into color photos, and that's how you do it.
So if you were just looking at it from a spaceship, you would see...
Oh no, you would be very bland. You must go, thank you.